diagnostics in application, diagnostic plots, residuals, all the types and flavors. It's the bread and butter, baby. What's your jam?
Greetings, Bio 6611. In this lecture, we're going to continue exploring simple linear regression, but specifically walking through an example with a continuous predictor variable. We'll first start by introducing the example, which we'll also use for a categorical predictor variable example next. We'll then see how we can do some of these calculations by hand, but then really leverage R to do a lot of the heavy lifting for us moving forward. So let's start with that motivating example. Let's say we have an investigator who's interested in studying endurance, and they want to specifically address two questions or research areas. One, to determine if VO2 max explains endurance during exercise, specifically the time required to complete a 2-mile run. The second question they want to ask, which will correspond to our next lecture, is to determine if there's a difference between males and females in physical endurance during exercise. A little more background: VO2 max, expressed as milliliters per kilogram per minute, is the maximum volume of oxygen that can be transported and utilized by the body during exercise. Specifically in this investigator study, we'll assume we have 20 subjects, 10 males and 10 females, who participated in a 16-week exercise study of 30 minutes of aerobic activity 5 days a week. At the end of the study, we'll measure VO2 max again using a treadmill test and then record the time to complete a 2-mile run in minutes. Here we can see our data set, a summary, scatter plot, and some other summary statistics. We see, for example, the first 10 values are females, the next 10 values are the male observations. We have then a column of information with the measured VO2 max, as well as the time it took to complete the 2-mile run in minutes. This information further is summarized over here at the scatter plot on the right-hand side, where we do seem to see a negative relationship where VO2 max increases leads to a lower time in minutes. Additionally, we've plotted the best fit line for that simple linear regression as well that we'll be calculating. Further, we can note the summary statistics below here, which we can use to calculate some of these beta coefficients by hand moving forward. So let's start by looking at those calculations for a simple linear regression setting by hand. So here we see we can use our summary formulas that we've introduced before to calculate our beta coefficients. Again, just for reference, we have those summary statistics that are of use in this context above. Taking that information, we can see that we can plug in these corresponding values and we estimate our slope parameter and our corresponding intercept for our regression fit. We see here that beta 1 hat, our estimated slope, does reflect that scatter plot we saw previously at negative 0.2099, and then our estimated slope beta naught hat is 24.22. Or put another way, we can write this out in our actual regression equation at the bottom of the slide here, where we can note that depending on your preference, we can either write plus that negative 0.21, or we can write minus 0.21. The one reason it might be nice to keep the plus a negative 0.21 is that it's very explicit then that there's that negative relationship for that slope term in case you happen to miss it was minus 0.21 x1. Additionally, we can also hand calculate the ANOVA table and fill in the various components. We're not going to go through this in too much detail here on the slide other than to note we can apply these different summary statistics we had before and the different relationships to calculate these quantities of interest. The other things we can just remind ourselves of is that the things like the mean square model and then the mean square error both are calculated by taking the sums of square equivalent and dividing by the degrees of freedom. What we'll see is that these quantities specifically will be useful to conduct hypothesis tests or to calculate different intervals, maybe confidence or prediction of interest. We'll be then applying some of these calculations as well as we put these results into the framework of the brief but complete summary of our results. So let's start with that complete interpretation for the first element, our point estimate. Now we're going to interpret this in the context of the slope, but we see our estimate for the slope, beta 1 hat, was negative 0.2099. Our interpretation then of this statistic on its own, or this estimate, is that on average, the time required to complete a 2-mile run decreases by 0.21 minutes, or maybe we want to translate that to a more meaningful scale like 12.6 seconds, for every 1 milliliter per kilogram per minute increase in someone's VO2 max. Again, the few things that are very important to note here is that we do stress that it's on average because it is taking all of our data into account and saying that on average this is the estimate of what we expect to observe. And it's also useful to note as well whenever we can to try to include the units that we're summarizing as well to provide that context for both x and y. In addition to a point estimate, we also want in our complete interpretation to provide an interval estimate of that point. In order to do this by hand, though, we first need to calculate the standard error for beta 1 hat in order to be able to calculate a 95% confidence interval. Here we're going to leverage the formula we've introduced in a prior lecture and plug in the relevant values to see that the standard error for beta 1 hat is 0.01857. Then we can take that and apply it into our framework for calculating a confidence interval, where we take the point estimate plus or minus a critical value times that standard error of the point estimate. Specifically here, because we are in our linear regression framework, we can go back to the fact that we know we're really referencing a t-distribution with n minus p minus 1 degrees of freedom. And that's how we get our 2.1009 critical value, which we plug in to calculate our confidence interval. Once we do that, we get our resulting interval and our interpretation that we are 95% confident that the time required to complete a 2-mile run decreases by between 0.171 and 0.249 minutes, or again, translating it back to maybe seconds, 10.4 to 14.8 seconds, for every 1 milliliter per kilogram per minute increase in one's VO2 max. So at this stage, we now have the point estimate and its corresponding interval estimate, but we still need to describe the uncertainty as well as our decision. So before we can make a decision about our slope, we do need to explicitly identify what the null or reference value would be that we're testing against. In practice, we can use any value of interest. It could be clinically motivated, scientifically motivated, or just something we want to try. However, most often what we're interested in testing is just, is the slope equal to 0? And therefore we'd have a hypothesis test of this format of h naught being beta 1 equals 0. By hand, we can note that for our simple linear regression model, we could evaluate the significance of this test in one of two ways, either using a t or an f statistic. We see above here a t statistic calculated with the form of beta 1 hat minus the null value for beta 1, which we've plugged in to be 0, divided by its standard error. We then know that in this case that would be approximately t distributed, again with our n minus p minus 1 degree of freedom for that 18. And if we take that critical value we see here, the test statistic of negative 11.3, and we compare it to a critical value, which we can just briefly note is down here in the interpretation, we would find that we have a p-value less than 0.0001. Alternatively, we could also calculate the overall f statistic and do an f test from our ANOVA table to test if any of the predictors, in this case just our single predictor of VO2 max, is significant in our model. Doing so, we could take that a mean square model divided by the mean square error. We see we have a fairly large statistic at 127.73, which is approximately distributed as our f distribution with 1 and 18 degrees of freedom, which would correspond again to a p-value less than 0.0001. Recall also from one of our past lectures, we have this relationship in simple linear regression where t squared will equal f. And so sure enough, if we take negative 11.3 squared, we do get approximately 127.73. Our interpretation then in this case is that a true slope of 0 is not consistent with our observed slope, since our t statistic is more extreme than our critical value, which is t at 18 degrees of freedom at 0.025. Here, because we're at a negative value, we're looking at that lower tail instead of the 0.975 of the upper tail. We thus, though, will reject the null hypothesis and conclude the slope is not 0. One thing we can note as well, and is more commonly done, especially when we have just a table of output with a p-value, is that we could just note since the p-value is so small and less than 0.05, we reject the null hypothesis that beta 1 equals 0 and conclude the slope is not equal to 0. The fourth and final quantity in our complete interpretation is some measure of uncertainty, which in many cases will be a p-value. And from the previous slide, we saw that p was very small and less than 0.0001. Our interpretation then of this value, that we can think back to our null hypothesis testing framework and how that came about from Fisher, Neyman, and Pearson, is that if the null hypothesis is true, and there is no association between VO2 max and the time required to complete a 2-mile run, in other words, if the slope truly is 0, then the probability of observing a slope of negative 0.210 or something more extreme is less than 0.0001. In other words, very unlikely if the null hypothesis is true, given the data we've observed and collected in this study. So the ultimate final step is to put all 4 of these pieces together into a short, concise summary. So we may say something along these lines that we see on the screen here. There is a significant decrease in the time required to complete a 2-mile run with increasing levels of VO2 max, p less than 0.0001. On average, the time required to complete a 2-mile run decreases by 12.6 seconds, with a 95% confidence interval of 10.4 to 14.8 seconds, for every 1 milliliter per kilogram per minute increase in VO2 max. Again, the nice thing about this complete interpretation framework is that we provide all this information of these 4 different pieces that we've highlighted their location in the summary, so that any person can make their own conclusion about the variability, the ultimate conclusion, or just the data that you've collected and presented. A final question that might be of interest to calculate before we move on to showing how we can do these calculations with R, is the amount of variation explained by the VO2 max. Again, this is getting at the idea that we may first say, well, what is an estimate of the variation in time required to complete a 2-mile run for any randomly selected individual? Or in other words, what's that variation here that we're estimating S sub y squared for just the outcome of time in minutes, that entire range of values? This then stands in contrast to what we're actually trying to do in a regression model, which is an estimate of the variation in time required to complete a 2-mile run for an individual with a given VO2 max value or predictor. In this case, we can almost imagine if we sketch on our figure here, we can draw the bounds around our predictors, and this distance between the two, that's going to be sort of presented as our S squared y given x, or that variation of y given some quantity of VO2 max. In this specific problem here, we see that the variation just overall in the outcome y is 3.026, and it's much smaller when we account for that VO2 max value. So one way we can quantify then how much smaller in the improvement that might represent is through our coefficient of determination, r squared, which we see here in our calculation as the sums of square model divided by the sums of square total, or equal to 0.8765. So what we can say is that 87.65% of the variation in 2-mile runtime can be explained by our VO2 max. So there appears to be a strong association between this continuous predictor of VO2 max and the time it takes to do a 2-mile run. And so with these by-hand calculations behind us, let's look forward to how we can use R to do these calculations moving forward, so we don't have to do all these things by hand. So let's introduce how we can do simple linear regression in R. And let's focus by breaking down some of this wall of text and code we see here for what we're going to see for results and summaries in the following slides. The first thing we have to do is somehow read in our data. In this case, we have a CSV file, but we could also imagine that we could make our own data frame based on the table earlier in the lecture for those 20 records. In this case, we're going to then fit using GLM, our linear regression model, for the outcome of minutes it takes to complete that 2-mile run and the VO2 max from the treadmill test. We'll save it in the object we're calling mod1 to reference the results in our plots and later on. Everything we see down here in our lower part of our code chunk is going to represent a 2x2 panel figure that includes some of these diagnostic plots that were discussed in a previous lecture, such as a scatter plot of just our actual observed data, a plot comparing our predictor with the jackknife residuals, a histogram of the jackknife residuals with the theoretical normal distribution that it could potentially achieve, as well as a plot of the PP, the observed cumulative probability to the expected cumulative probability, which again is similar to a QQ plot, but with just a slightly different way of calculating and presenting the potential association. So let's start by walking through our diagnostic plots and note if there's anything that seems like a departure from some of our assumptions. What we can note from our scatter plot on the top left is that there generally does appear to be fairly similar variance across our different values of VO2 max, or x, for our outcome y. This is further reinforced by our residual plot in the top right, where we see that there's a fairly consistent band. There's not really a fan or funnel pattern happening in that figure. In the histogram of our jackknife residuals, we see that it's a little hard to interpret considering we only have 20 observations, but it does seem like they're at least centered around 0 and contained mostly within -2 to 2. So most of the data falls within the range we would expect. And finally, we can see the normal probability plot mostly follows that diagonal line, suggesting that normality is probably an okay assumption to make here, even if we do have a fairly small sample size of 20. One thing we can then do, instead of all of our calculations by hand to arrive at that fitted regression model, is to take our summary of mod 1, that object that we stored our GLM results in, put a $, and then pull out the object called coefficients. And that's going to explicitly call out and present to us the coefficient estimates for beta naught hat, beta 1 hat, its standard error, its t-value test statistics, and its p-values. We can again note from the output above here that we actually have the same fitted regression equation that we got by hand before, and similarly we have t equals -11.3 with a p-value that's extremely small, less than 0.0001, like we calculated previously. A few things that are useful to do here rather than by hand are some of these confidence and prediction interval estimates that we looked at previously deriving the equations for by hand. But we can do so in R with some functions that will make it much more efficient. For example, we might say, what is the average time required to complete a 2-mile run for a large group of individuals with a VO2 max of 50 milliliters per kilogram per minute? And what is an interval estimate for this average time? Now here we're focusing on that large group of individuals, so we want to calculate a confidence interval estimate. And here we know that we can use that fitted regression line on the previous slide, add a value of 50, plugging in for x, or in this case saying x naught, and we can calculate that the average time to complete a 2-mile run for a large group of individuals with a VO2 max of 50 milliliters per kilogram per minute is expected to be 13.73 minutes. However, this only answers that first question and not the interval estimate. For the interval estimate, we can take now advantage of R to do the work for us. Now there are a few caveats if we're trying to stick with base R functionality. Instead of using GLM, we will have to fit the model again with LM. And this will then allow us to use the predict function to specify the new data, where we just say a data frame with the predictors that we wish to specify the prediction at. In this case, it's just a VO2 max at 50. And then we also have this additional argument where we specify that we want a confidence interval around that estimate as well. In the output that comes from that, we can see we also get that fitted value we had on the previous slide, as well as our lower and upper intervals, where we can interpret that as we are 95% confident that the average time to complete a 2-mile run over a large group of individuals who have a VO2 max of 50 milliliters per kilogram per minute will be between 13.35 minutes and 14.11 minutes. We may also wish to ask, well, what sources again of variability are contributing to our uncertainty around this estimate of a 2-mile run time with a given VO2 max for a large group? In this case, we would say that the error estimating beta naught and beta 1 and the distance of our predicted value x naught from the mean of the predictor x are those contributing sources of our variability. Here, the individual variability is not being contributed around x. This then leads us to a related and similar question for the prediction interval estimate, where we may wish to ask instead, what's the predicted time required to complete a 2-mile run for an individual who has a VO2 max of 50 milliliters per kilogram per minute? And then what's an interval around that time for an individual? Again, it turns out that that predicted fit will be the exact same value for an individual as it will be for the entire group. So the average time to complete a 2-mile run for an individual with a VO2 max of 50 will also be expected to be 13.73 minutes. The difference here, though, will be in the prediction interval, which you've seen previously will be wider. So again, we're going to use the same setup we saw before, but we're going to make a slight twist where prediction will now be specified for interval instead of confidence. By doing so, we see here in our output, we get the fit of that value we saw in the previous slide, as well as the 95% prediction interval. So our interpretation here is that we are 95% confident that an individual with a VO2 max of 50 milliliters per kilogram per minute, assuming no error in measuring that VO2 max, will complete a 2-mile run in between 12.36 minutes and 15.1 minutes. Again, we have to note that for our prediction interval, because it's based on a single individual, we do have to make our assumption about normality and the distribution being correctly measured. We can also note just briefly that the sources of variability contributing to our uncertainty in this interval are similar to before, with the error in estimating beta naught and beta 1 and that distance from our predicted value of interest x naught, or that predictor of interest, to the mean of x, but also the individual variability around the mean of y given x. Now we're trying to take into account that individuals will vary around each prediction. One final thing that can be helpful in this case would be a figure representing the confidence interval and the prediction interval. Here we'll do so with ggplot, and we just have the code listed here, which outlines some of the calculations in the setup that we'll see on the following slide for the resulting figure. And here on the figure, we see our dashed red lines represent our 95% prediction interval because it's wider. That blue solid line represents our best fit linear regression line. And then the shaded area, the confidence band, is really our confidence interval region. A few things again we can note is that we have narrower widths when we're closer to the mean of our predictor VO2 max, and it gets wider as we get further away. Also, what we can note is that the prediction interval is fairly wide across, but also has a similar pattern where it gets slightly less wide near those means of interest. And so with that, we'll wrap up this lecture about a continuous predictor example, and in the next one, we'll focus on a categorical predictor.